Okay, so I'd like to begin the afternoon sessions, and our first speaker is Jianxin Pan, and he's going to be talking about large sample covariance matrices for the t-squared statistic.
In the last few days, a lot of our speakers have been talking about high-dimension data. When dealing with high-dimension data, people always face sample covariance matrices. Now I'm going to talk about sample covariance matrices. This is joint work with Joe. In statistics, the sample covariance matrices is defined by capital S if we ignore the difference, minor difference between n and n minus 1. However, in the random matrices framework, instead of capital S, we usually consider capital S1. And then you might wonder what is the difference between capital S and capital S1. In the large dimension case, there is no much difference between capital S and capital S1 if we are only concerned with empirical spectral distribution function and some asymptotic probability of extreme eigenvalues. But at the end of this talk, I'm going to say a little more about this capital S and capital S1. Here we assume the large dimension. What is the large dimension? Large dimension means the dimension P of random vector is comparable to the sample size. Now, what is the difference between large dimension and fixed dimension? Here are some examples. The first example is about statistic capital Wn, which is useful in multivariate analysis. If the dimension P is fixed, then it's very easy. By Taylor expansion, one can prove that after scaling, capital Wn is asymptotic normal. But what happens in the large dimension? Unfortunately, this is not the case in the large dimension. In fact, by the theory of random matrices, one can prove this quantity now converges to minus infinity. So any hypothesis testing which assume this statistics is asymptotic normal, then will cause serious error. This is a histogram of this statistics. As we can see, even the ratio C is as small as 0.2. The histogram of capital Wn shift left from right side as the sample size increase. So this is again confirm what we said at the end of this slide. The second example, suppose the population matrix sigma has a spectral decomposition. Here lambda is eigenvalue, ui is eigenvector. In classical multivariate analysis, we know that sample eigenvalue is a consistent estimate of population eigenvalue, and also sample eigenvector are the consistent estimate of population eigenvector. Again, this is not the case in the large dimension. Prof proves that the extreme eigenvalue converges to fixed value, which is different from 1 if the population matrix is identical matrix. And also Johnston and his course has already proved that the population sample eigenvector is not a consistent estimate of population eigenvector. Random matrices nowadays has a lot of application in other subjects like finance, virus communication, and the large linear system and sparse problem. The most popular tools in random matrices is Statistical transform. As we can see, Statistical transform define the integral with respect to distribution function gx. It's like Cauchy transform. It's like Cauchy transform. The advantage of Statistical transform is that the function of eigenvalue can be transformed to the random matrices itself, because as we know, it's very hard to work on the individual eigenvalue itself. Now, why state transform works? There is a famous, This famous inversion formula for Fourier transform. So, the convergence of Fourier transform is equivalent to the convergence of corresponding distribution function. That's why Fourier transform works. So in this sense, Fourier transform is correspond to the characteristic function. There are a lot of other methods like moment method and orthogonal polynomial operator theory, and so on. Now we skip it. Now let us have a quick look at what the main subject are in the random matrices. Obviously, when we talk about the random matrices, we are mainly concerned the eigenvalue and eigenvector. The first fundamental object in the random matrices is the empirical spectral distribution function, which is defined as indicate function of eigenvalue. The importance of empirical spectral function is that the sum of eigenvalue can be transformed integral with respect to empirical spectral function. So if we know some properties of empirical spectral function, then we can make statistical inference about the summation of eigenvalue. Now there are some authors that prove that the empirical spectral function of a sample covariance matrices converges to with the probability 1 to a fixed distribution which has an explicit density FCX. No matter what the population distribution is, as long as we have some moment condition like second moment finite. This is about the extreme eigenvalue. So from this result, you know that now eigenvalue is not a consistent estimate of population eigenvector, population eigenvalue. This is about the asymptotic distribution of extreme eigenvalue by Johnston. This result is about the Wishart matrix in the real case, in the complex case, which is done by Johnson. Now, about the central limit theorem of eigenvalue by and Silverstein, we have some result in this direction. Regarding eigenvector, on the one hand, in order to investigate whether the eigenvector has an asymptotic hard distributed, Silverstein and Bai, and we have such result in this direction. On the other hand, Johnston and his co-author has proved that the sample eigenvector is not consistent estimate of population eigenvector. Also proposed a new method about how to estimate. About eigenvector, I should say there's still a lot of things unknown. Now let us go back to our today's topic. We noticed that the sample mean SE bar and the sample covariance matrices capital S are independent if the element Xij are ID normal. Somehow, we believe that sample mean and sample covariance matrices might be asymptotically independent in some sense under general distribution instead of Gaussian distribution. Maybe you wonder why you should have such a belief. First, as you might know, a lot of asymptotic properties of sample covariance matrices are robust, like the empirical distribution function, the convergence of empirical distribution function doesn't depend on the population distribution. Or eigenvector of sample covariance matrices is very similar to eigenvector matrices of Wishart matrices. And a little bit later, you can see we provide some evidence to support this. Now, another motivation is Hurtering proposed a t-square statistics. We know that if capital Xij is from normal distribution, then since SE bar is independent of capital S, then it's very easy to derive the central limit theorem of T square. But what happens in the general case? It would be desirable if we know what the limit distribution is in the large dimension case. Now, the idea is how to formulate this problem if SE bar and capital S have some kind of asymptotic independence. To be honest, so far we have no idea how to formulate this problem in a mathematical way. So we propose to investigate the random quadratic form involving sample mean and sample covariance matrices. What we have in mind is that if sample mean and sample covariance matrix is independent, then this random quadratic form, the asymptotic distribution of this random quadratic form should be independent of SE bar, or more generally, if we replace one of SE bar in this random quadratic form by any fixed unit vector, again, the asymptotic distribution of the new random quadratic form should be independent of SE bar. As it turns out, this is true. This is our main result. First, we suppose Xij is IID and with some moment condition. And also, we suppose Gx is kinetic function, Gx fx analytic function. Then we prove that these two-dimension random vector converges to two-dimension Gaussian random vector. More importantly, we should notice that x is independent of y. So, based on this result, roughly speaking, if given SE bar, then the first random quadratic form, the asymptotic distribution of the first random quadratic form should be the same as the second. The second is we replace SE bar by any unit factor. So this provides strong evidence to support our conjecture. Now from theorem 1, if we take fx is equal to 1 over x, then it's very easy to get the central limit theorem for heterogeneity statistics. Now, as you can see, the asymptotic distribution is not chi-square anymore in high dimension case. Now it's normal distribution. Now this is our last slide. At the beginning, we said that there are no much difference between capital S and capital S1 if we are only concerned with empirical spectral distribution function and the asymptotic property of extreme eigenvalue. Now, from theorem 1, we can get the central limit theorem for the capital S. From theorem, we know that from this corollary, we know that the central limit theorem for capital S and capital S1 are different, which is not the same. At the beginning, this is a little bit beyond our expectation. Normally, we know that the minimum eigenvalue or maximum eigenvalue of capital S and capital S1 are the same. And also, we have another work discussing the asymptotic relationship between capital S and capital S1. We know that the asymptotic property of eigenvector of capital S and capital S1 are very similar, but the central limit theorem for the eigenvalue are completely different. Okay, thank you.
Great. So we have 2 minutes for questions. Any questions? Art.
Can you back up to your normal limit slide? It went by too fast. Okay, so I was trying to check whether the mean was somehow equal to half the variance, but it doesn't look like it is. Okay. Yeah, so it's really different from high school.
Yeah.
Anything else? Well, let's thank Guangmin again.